Before we start our tutorial video today, if you love our videos, please click on like button, and make sure to click on subscribe and bell icon, to receive notifications for future helpful content of automation and control. Now let's get started. Pressure and differential pressure transmitter features. Main components. Pressure is measured by means of transmitters that generally consist of two main parts, a sensing element, which is in direct or indirect contact with the process, and a secondary electronic package, which translates and conditions the output of the sensing element into a standard transmission signal. Main components of P or DP transmitter will be as the following. Secondary electronic package. Push buttons to manipulate the parameters. Housing cracking. Front windowed cover. Standard LCD display. Terminal block. Rear cover. Sensing element. Primary electronic. Transducer body. Transducer gasket. Isolating diaphragms. Measuring principle. The most common effective sensing methods used today are electromechanical strain gauge, variable capacitance, variable reluctance, and piezoresistive. Each of them having certain advantages and disadvantages includes various types of sensors, offering the combination the best performances of each of them. Electromechanical strain gauge. Electromechanical strain gauge sensors convert pressure into relatively small resistivity changes. The change in resistance typically affects the four legs of a Wheatstone bridge circuit. Variable capacitance. Variable capacitance transducer sensor operates as follows: an increase in pressure on the process diaphragm is transmitted through the fill fluid to the ceramic diaphragm in the capacitance sensor. The pressure increase causes the diaphragm to bulge, thus changing the distance between the diaphragm and the reference plate. This change in distance is very small. The change in the ratio of the C- and C+ capacitance feeds the logic circuit of the transmitter. Increased output from the logic circuit is converted to DC voltage and amplified by the gain and summation circuit. The signal from the gain and summation circuit is applied to the output current regulator through the zero and span circuit. The output current regulator produces an increase in transmitter output current, which is proportional to the increase in process pressure. Piezoresistive. Piezoresistive sensors have come into wide use in recent years. They can be considered the semiconductor technology version of the electromechanical strain gauge that we have already described. The piezoresistive sensor consists of a semiconductor element that has been doped to obtain a piezoresistive effect. Its conductivity is influenced by a change, compression or stretching of the crystal grid, that can be produced by an extremely small mechanical deformation. As a result, the sensitivity of monocrystalline sensors is higher than that of most other types. In particular, higher than the standard strain gauges, whose resistance changes only with geometrical changes in the structure. Signal transmission. As already mentioned, the secondary electronics of a transmitter amplifies and conditions the weak electrical signals generated by the sensor, so that the signals can't be sent long distances without being degraded by noise, and so the signals can be used to drive devices such as indicators, recorders, and controllers. Transmitters use several techniques to transmit their signal. This tutorial describes 4 different types of signal transmission. 4-wire transmitter, 2-wire transmitter, smart transmitter, and fieldbus transmitter. 4-wire transmission. In 4-wire transmitters, 2 wires are used for power to the instrument, and the other 2 wires are used for signal transmission. They are used in special cases such as in remote areas where commercial power is not readily available. In these cases, the transmitter will be powered by an alternate power source such as a battery or perhaps even a solar cell. For most applications where commercial power is readily available, the two-wire transmitter is the practical instrument, because of the added cost to install and run 4 wires to a transmitter compared to 2 wires. Two-wire transmission. Two-wires transmitters are designed to provide a current transmission signal of 4 to 20 mA DC. The majority of electronic pressure transmitters available today are two-wire devices. A two-wire transmitter uses part of the 4 mA bias current to operate its electrical circuitry. Both power and signal are carried over the same 2 wires. Current transmission is used because a current signal can be carried over long distances without being affected by circuit resistance that can change depending on length and temperature, as well as the quality and number of connections. Smart transmission. Intelligent or smart transmitters transmit both digital and analog signals over the same 2 wires. A digital signal is superimposed over the traditional 4 to 20 mA. Digital signal transmission is faster and more accurate than analog. More information can be carried between the instrument and the control room using the same 2 wires with two-way digital transmission, including configuration and diagnostic information. Two-way communications means that a value can not only be read from the end device but it is possible to write to the device. Fieldbus transmission. Fieldbus is a digital, two-way, multi-drop communication link among intelligent control devices that can be used only instead of the 4 to 20 mA standard. Multi-drop communication means that over the same 2 wires can take place a digital communication among several field devices, like valves, pressure transducers, etc., and computers, programmable logic controllers, PLCs, or remote terminal units, RTUs. The multi-drop capability of a fieldbus will perhaps result in the most immediate cost-saving benefit for users, since one single wire pair is shared among several devices. While with analog or smart devices, a separate cable needs to be run between each end device and the control system. Thank you so much for watching and have a nice day.